Hello everyone, I'm Rasoul.Kheiri from Skolkovo, Moscow. This is a presentation for physical mesomechanic of condensed matter conference in Tomsk. And the title is velocity dependence of the dry sliding friction at the nanoscale. So tribology or friction. In tribology or friction, people use atomic force microscopy for experimental tool. There is a tip and there is a sample as a surface, and then there is a cantilever. So the tip moves on the surface, and there is detectors that can track the movement and for different purposes, including friction. Alternatively, people use modeling and molecular dynamic simulations for these models. Experimental tools and molecular dynamic modeling and mathematical modeling can help us to understand the phenomenon better. For example, in the experiment, the interface between the tip and the sample is buried. So there is no information when the tip moves on the surface. We can't see what's the interaction between the tip and the surface. For this reason, molecular dynamic simulations can help us to understand better the interface layer of sliding. In our model, we have a nanoparticle moving on a stack of several layers of graphene. For the nanoparticle, we prepared the nanoparticle from aluminum atoms, almost 32,000 of aluminum atom gathered together, and the 10 graphene layers, and the bottom layers is frozen. A vertical force will be exerted to the particle. A horizontal force will be exerted to the particle. The vertical load is approximately the normal load. We notice that the normal load can be different from the applied load, and that is important even in the absence of adhesion. And the horizontal force is here to give the particle acceleration and velocity to the surface. Okay, in the equation of motion, we assumed a linear viscosity of damping or friction, like in liquid. And it's interesting because solid friction, according to the Coulomb law of friction, solid friction is independent of velocity. But here we will see that friction at the nanoscale can be different, and even opposed to the Coulomb laws of friction that are macroscopic. So in addition to the linear damping force, like in liquids, here we have a random force. The random force can move the particle in its direction of movement, and but the average of the random force is 0. So as a good postulate, for this, the average of the velocity can be derived by solving the differential equation, and after a while we see that the particle will reach a steady state velocity, a constant velocity. At the right we have an example of two realization when the particle after a while will reach a constant velocity. The vertical axis is velocity and the horizontal axis is time. To build the molecular dynamic potential, we need four kind of potential or a complicated potential of many body forces to consider these interactions. So in the here we see four types of interactions: interactions between graphene, interaction between graphene layers, interaction between aluminum atoms, and interaction between aluminum atoms and graphene carbon atoms in the surface. By this model, we want to simulate our study with LAMS software. LAMS software is a molecular dynamic software available and everyone can use it. Okay, at first we build a cubic FCC lattice from aluminum atoms. Then we remove particles from a spherical region to have a spherical particle and gather the data for the spherical particle. After building graphene layers with VMD software and also aluminum spherical lattice of nanoparticle, we gather all to one system and perform equilibration with a normal load. So here there is a video showing how equilibration happens, and I explain on the video. So as we can see, the particle, there is a normal load applied to the particle, and particle come to the surface. We use box relax and minimization. We set the bottom layer frozen, and the most important part is NPT, that is barostotic at the constant pressure for our system. So far we have an equilibrated system with a normal load applied to it. Then we want the next step is performing molecular dynamic simulations. So we noticed that the particle shouldn't be overloaded. We see that for some forces, huge forces, the particle can match to the surface, and it's not good because in the spherical particle has lost. So there is a range for applied forces. Here the ranges are a range of applied forces for the vertical force normal load is shown that it should have an upper limit. So for potential between carbon atoms and carbon, aluminum atoms, we use the COM3 many-body potential. This potential is the 3 generation of COM potential. And COM potential is charge optimized many-body potential. And there are 4 terms of electrostatic, short range, van der Waals, and correlations. So this potential has an advantage that can be used for all types of potential, CC, carbon-carbon, AL, and ALC. As an advantage, COM potential is exact potential. So if the result can be exact, reliable, but it's also time costing. So there is a comparison here between Lennard-Jones and COM potential. And we can see here that for a particular case, COM potential is 250 times slower than the Lennard-Jones potential. So it's as a disadvantage or as a point, these potential can be time costing, but the advantage is that it's a good potential here referred to the machine learning potentials. So it's it shows that it's exact potential. Another issue that we solved during the simulations is horizontal movement of the surface. For preventing the surface to have horizontal movement, when we apply the horizontal force to the nanoparticle, we used the same code for impacting of gold to graphene layers. To edge the 2 fixed edges. So this green colored shows the edges. So we fixed edges in beside the bottom layer. We also fixed edges to prevent the surface to move with the particle. After all, we have MD simulations. MD simulations means that a thermostat applied to the particle, and there is a time integration for evolution of equation of motion. So here is a video for molecular dynamics simulations. We see that the particle moves toward the right, where the applied tangential force is applied to the particle. We have a periodic boundary condition in the movement of the particle. And in this example, normal load is around 50 nanonewton, and tangential force is around 5 nanonewton. for the result. After some time, we see that the particle will reach to a steady state. And for this particular example, the particle will reach to a steady state, nearly a steady state, in around 2 nanonewton. So generally, after a few nanonewton, the particle will reach nearly a steady state when the particle will continue to move in a constant velocity. Then we gather data. In this point, we record the velocity of a steady state to see the friction coefficients relation to the velocity. Here we have friction force versus velocity. So these velocities are gathered from steady state velocities. For each point, a particle moved, reached a steady state velocity, and the steady state is recorded, and the horizontal force also recorded. This continued for realization. Then the normal load changed, and again velocities of a steady state regime gathered, and all together we see that a linear dependency of friction force on velocity. So here we have for different normal load and also for different horizontal force. That the point is that horizontal force is equal to the friction force at velocity of a steady state. So at a steady state velocity, the horizontal force exerted to the particle is equals to the friction force. We prepared a manuscript for this result and submitted to the conference proceeding to be peer-reviewed for the terms physical mesomechanics conference. For future studies, we can perform simulations for normal load dependency of friction coefficient. We can perform simulations for different temperatures. Today, we showed simulations in room temperature 300 Kelvin. We can change the temperature and study the thermal activation. Quantum friction coefficient can be theoretized, and so in a theory we can make a comparison between classical and quantum features, and what is the influence of a quantum surface on the movement of a particle. And then maybe in simulations we can add also electronic part of friction coefficient. After all, I thank you to my supervisor, Professor Nikolai Brilliantov, my advisor, Alexei Tsukanov, PhD committees, Alexei Vishnyakov and Alexei Shapik. Also, a friend of mine from Skolkovo, Ilya, we had some discussions about molecular dynamics simulations. After all, I thank you everyone who the, made attention to my presentation, and thank you to the physical mesomechanic Tomsk conference for the opportunity